10.2 Taylor series. Threw a ton of fun at you in unit 10.1, where we introduce power series, which is stuff that kind of looks like this, but it goes on forever. So now we're getting to Taylor series, which are much more specific, and they're built a very specific way. So we're not reliant on a geometric and integrating or taking a derivative geometric. We can make them this other weird way. I'd like to apologize. I did not leave you nearly enough space here, but check it out. Power series, A0 plus A1 times X, A2. If it's centered at X equals 0, and I know what's going on when P equals 0, which I gave you here, and you're like, where'd all this come from? This is just an example to get you warmed up. We'll get to the point where we build it ourselves very soon. Okay, so then if X equals 0 and I know what P of 0 is, I've got A0. That's what we're going to do. Then we're going to take a derivative. That'll vanish. This will become just A1. This will be 2ax plus 3ax squared. Well, if x is 0, they all vanish, and I can find out what a1 is because I know what p prime of 0 is, so on and so on. So, again, with apologies for space, p of 0 equals 5. Plugging in 0, these all cancel. Then I know that a0 equals 5. You might think, well, they're all just, then it's 7, 11, 13. Plug them in, we're done. Yeah, we'll see. P prime of 0 equals 7. And if we do it up here, we get A1 plus, and this is time consuming because I need to be careful, 2a2x plus 3a3x squared plus 4a4x to the third. Knowing 0 goes in, we know that a1 equals 7. Keep going. P double prime of 0 equals 11. Taking the next derivative, a1 vanishes, x vanishes, we get 2a2 plus 6a3x plus 12a4x squared. Plug in 0 by, we find out that, check it out. Now we got to divide by 2. A2 equals 11 halves. Third derivative equals 13. 1, 2, 3, yep. Very tedious, a lot of time. Derivative by derivative 6a3 plus 24a4x. That equals 13 when we plug in 0, divide by 6. A3 equals 13 over 6. Keep going. P4 of 0 equals 17. Take the derivative. 24a4 equals 17. A4 equals 17 over 24. Okay. So there it is. Now, I know what's going on with all these derivatives. I can find out what this is. Why would I do that? Well, I'll show you in a little bit. So P of x equals 5 plus 7x, because we figured out a1, plus 11 halves x squared plus 13 over 6 x to the third plus 17 over 24 x to the fourth. There it is. Given all these derivatives, we can write a Taylor series, which is a type of power series. It's got it all set up. That goes on forever and ever. If we find a pattern. Here, there's no pattern. Although I do notice this is over 1, this is over 2, this is over 3 times 2 times 1, this is over 4 times 3 times 2 times 1. We're going to end up with a lot of factorials on bottom problems. At this point, somebody usually says to me, oh, factorials actually are useful. I thought they only got used in probability, which is the most worthless of the, they're useful. So now I'm not giving you the derivatives or the P naught, whatever. We're going to go figure it out. We're going to say, let's make an equation that looks like this, can approximate this. Because natural log is just magic in my calculator. This is really what we're getting to. How does your calculator do natural log? It uses this. We came up with natural log a different way. Let's see if we get the same answer. I believe we said, no, I'll do that later. So here we go. Let's see, I gotta do a bunch of derivatives if I'm not mistaken. Well, not yet. Plug in 0 and I get a naught. Plug in 0 and I get ln of 1 plus 0, which is 0. A naught is 0. That was weird. Okay. P prime of 0 equals, I'm going to shortcut derivative by, derivative has x, they're all going to vanish, just a1. Now what's the derivative of natural log? 1 over 1 plus plug in 0, 0 equals 1, a1 equals 1. Hey Ma, I'm doing calculus. P second derivative of 0, based on what we did up above, is 2a2. Now, I think I'll go over here and do a bunch of derivatives. Ln of 1 plus x, derivative of ln of 1 plus x is 1 over 1 plus x. Derivative of 1 plus x to the negative first is negative 1 over 1 plus x squared. Derivative, I think I only need to do 1 or 2 more of these, of negative 1 plus x to the negative second is 2 over 1 plus x to the third. I think I have to do 1 more over here, but I'll come back to that. 2a2, where are we on this list? This is so confusing. 0, 1, oh, so we're just right here. That's a piece of cake. Negative 1 over 1 plus 0 squared. So, looks to me like a2 is negative 1/2. Why are we doing this, Mr. T? I don't understand. I'll get you there. This is how your calculator approximates. 1, 2, 3 of 0. Up above, we saw that taking the third derivative and plugging in 0 right here, I think. 1 is 3 and 2 is 6. And third derivative is just 6a3. The x is gone. 6a3. Okay, third derivative, 1, 2, 3. Yeah, is 2 over 1 plus 0 to the third. A3 equals 1/3. Wow, almost looks like I know what I'm talking about. I'll try not to let that happen again. Fourth derivative, and I didn't do it yet. Let's down this a little. D dx of 1 plus x to the negative third equals negative 6 over 1 plus x to the fourth. Fourth derivative, hope you knew that's how they write derivatives once they get above 3, equals, well, it wasn't 6a3, it's 24a4, which is negative 6 over 1 plus 0 to the fourth. A4 equals negative 1/4. I see a pattern. 0, whatever, 1, negative, positive, negative, 1/2, 1/3, 1/4. I bet I could write out the entire thing for ln of 1 plus x. We have only said, let's just do this many terms. So ln of 1 plus x approximated with fourth order polynomial. This is going to pop up in your near future with 1, 2, 3, 4, 5 terms, but a fourth order polynomial. equals 0 by 1x plus negative x squared over 2 plus x to the third over 3 minus x to the fourth over 4. There it is. Didn't we do something where we said 1 over 1 plus x equals 1 minus x plus x squared minus x to the third, dot, dot, dot. And then we integrated it. And we said that's ln of 1 plus x, technically with a absolute value. And we integrated, we got x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4. Hey, that's pretty cool. So several people will say, well, why don't we just do this? That seems a lot easier since I knew what was going on in geometric series. Well, no, I mean, just picked an example that works. They don't always work. I don't know how I would do sine or cosine with a geometric. This just happens to be the case. I can build this one geometrically or with a Taylor series construction technique. Nice news is that we get the same answer. And you need to memorize this. What's ln of 1 plus x? This and dot, dot, dot. And the nth term is x to the n over negative 1. Yeah, whatever. Another time in your near future. So we just constructed the fourth order Taylor polynomial for that function. Taylor series never ends. Right, we have a Taylor polynomial. What is the Taylor series? What's the seventh order Taylor polynomial for sine of x? Well, sine of 0 equals 0. Derivative of sine is cosine. Cosine of 0 equals 1. Derivative of cosine is negative sine of 0 equals 0. Derivative of negative sine is negative cosine of 0 equals negative 1. Derivative of negative cosine is sine of 0 equals, and I think I'm seeing a pattern here, but I didn't write them down. This is just the p of 0. This is p second prime of 0. This is p prime of 0. This is p third prime of 0. And hopefully that's 3 tick marks. I'm not going to worry about it. And p of fourth of 0. And we know what's going to happen after that. It's just going to alternate 0, 1, 0, negative 1, 0, 1, 0, negative 1. Okay, so just plug it into the stuff you were doing. Wait a minute. What do you mean just plug it in? Plug it into here? P of x equals a naught plus a1x plus a2x squared, a3x to the third, a4 the fourth plus a fifth x to the fifth, holy cow, plus a6 x to the sixth plus, this is a little tedious, a seventh x to the seventh. Goodness gracious, what did I write there? A7 x to the seventh. Weird. No, it's supposed to be subscript. Anyway, you get the idea. All right, slow down. All right, so this is the first term. So P7, we throw a little subscript on there. 0. This is 1, and it was still 1. But then when we did this, all these terms, because of the derivatives, started dropping by factorials. So the next one would be 0x squared over 2 factorial. Well, who cares? Plus the next one would be negative x to the third over 3 factorial. Plus the next one is 0 again. 0x to the fourth over 4 factorial. Plus 1x to the fifth over 5 factorial. Plus 0x to the sixth over 6 factorial minus x to the seventh over 7 factorial. In other words, sine of x approximated with 7th order Taylor series polynomial equals, throughout all the zeros, x minus x to the third, 3 factorial plus x to the 5th, 5 factorial minus x to the 7th, 7 factorial. A lot of work to get to that point. Hopefully we don't have to do that again. No, you don't. You don't. You don't, because once we've done this, we're going to memorize this. And you're going to probably say, how the hell would I memorize that? Well, sine is an odd function. So it's x to the first, third, fifth, seventh. It alternates, and it's got factorials on the bottom. That's it. And this actually works. This not only actually works, this is how your calculator does it. Sine of x is the sum. Here, let's start at 0. Why 0? Why not? To infinity. -1 to the n. X to the 2n plus 1. Mr. T, I can never figure this out. How do you know that? Because I've done it before, and I'm cheating using my notes. So after you've seen it a few times, you get there. And then you check. Plug in 0. Get 1 factorial. Yeah, that's fine. I get that. I get 1. So the first term is x. Cool. Second term, 1. The next term, the first term. 2 plus 1 is 3 factorial. Nice. 2 plus 1, x to the third. Nice. -1 to the first. Nice. It works. That's how your calculator calculates sine. You put a number in and off you go. So this is centered at 0. So it's called the Maclaurin series. Taylor is the general name, hot tub. Maclaurin series is a specific type of Taylor series, jacuzzi. Hope that made sense to you. A lot of people immediately know what I'm talking about. If you don't, you really need to learn to read my mind, then you'll be good to go. So the partial sum is that Taylor polynomial we were talking about for f at x equals 0. Partial sum, the first 4 terms, the 7th order polynomial, whichever. Watch it. I always get caught by those. They're tricky. All right. How about cosine? I happen to know that cosine is an even function. So it's 1x to the 0. One x to the 0, which I don't write, and it alternates just like sine, x to the 4th minus x to the 6th, so on and so on. Oh, wait, we wanted to know what cosine of 2x is. That's a piece of cake. Cosine of 2x equals 1 minus 2x squared plus 2x to the 4th. Yeah, literally, you just plug it in. 2x to the 6th. Oh, wait, it wants the 4th order. All right, get rid of that. So the 4th order polynomial, so that's his 4th order polynomial, is 1 minus, and you can write this however you want. I would never in a billion years cancel, because then you won't see patterns. 16x to the 4th. You could have left it inside just like this, but I feel like throwing it out. X to the 4th over 4 factorial. If you wanted, you could cancel that out and say, well, it's 1 minus 2x squared plus 2x to the 4th over 3. But I wouldn't do that. I think that's crazy. Cool, huh? It's cool. There's no other way to describe it. It's just neat. Okay, how many terms required to approximate? I don't know why you set a 13. That's a crazy number. To sine of pi over 2. That makes a lot more sense. Sine of pi over 2, according to my calculator, is 1. So now we're going to put those terms in. So the sine of pi over 2 approximately equals x minus x to the 3rd over 3 factorial plus 5 factorial, dot, dot, dot. Now I want it to 3rd decimal place, so this needs to get to 1.000. And I better check that 4th place, make sure it's not 5 or 6, 7, 8, 9, and rolls over. So yeah, just not, hey, you get to use your calculator. You have to use your calculator. So see if I can do this intelligently. I doubt it. I don't really trust myself. There's pi over 2. So that, what's the first one? Minus, oops, told you I couldn't do it. That to the third divided by 3 factorial, 3 times 2. That's the first 2 terms, 0.924, not bad. Let's add in that next term, plus, no, parentheses, pi divided by 2 to the 5th, divided by 5 times 4 times, isn't there a factorial? Yeah, there is, but it's easier to do that. Ooh, we're getting closer. Let's add another term, minus, notice how it's oscillating below 1, above 1, below 1. The next one should get below 1 again. Pi over 2 to the 7th over 7 factorial. Now let's see what we got. So minus pi over 2 to the 7th divided by, yeah, I think I'll do 7 factorial this time. 7 math, oops. Would have been a lot smarter to go that way. 4 factorial, 0.9998. That's actually it. This equals 0.9998, which is, if I round to 4 decimal places, 1.000. So it needed 4 terms, or it needed the 7th order polynomial to be accurate to 3 decimal places. So back to, how does your calculator do that? Well, it does that very thing, and then it has a little bit of logic built in saying, take any term and subtract the previous term. If you get less than 0.0000, whatever number of decimal places, I think it's 7 or 8, if the value is less than the 9th decimal, 0.00000001, whatever that works out to, it stops calculating and throws the answer up. And that's why your calculator does do this cycling thing where it's taking a while. It's doing a lot of math. It's cranking these out. Even in transistors, it takes a little time, right? So now that you're probably like, okay, I kind of understand that, let's make it harder. You know, that's what we do. So what if we didn't center it at 0? What the hell does that mean? It's not a big deal. It's just that thing we had earlier, and some n factorial, a naught plus a 1 x minus a, centered at a, plus a2 x minus a squared, plus a3, yeah, I'll do one more, x minus a to the 3rd plus dot 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 a n x minus a to the n. So we can build one like that. Here's the good news, very rare. I see it, I do see it. It's not in, I would expect to see it on your AP test, but mostly they're going to focus on the ones that are centered at 0. All right, why do this? Well, the reason I didn't do 13 is this thing is way, I would have needed like 90 terms to do that. The factorial would have to get really, really big to get it down. It starts oscillating at first. You get these really big, huge numbers and really big, small numbers. And after a while, when the factorial starts to dominate, become really massively huge, then it starts getting back to reasonable. So I picked in one that's pretty close to 0. This is centered at 0. But hey, I want to do 13. You'd put in 13 here and it would get there a lot faster. This is just a technique to approximate numbers much more quickly. All right, let's do the Taylor series generated by e at x equals 2. I happen to know e to the x. Trust me on this one, and we'll explain why later. Plus x squared over 2 factorial plus x to the 3rd over 3 factorial, dot, dot, dot. Now we want to do it at x equals 2. Well, we need some derivatives. So it'd be e to the x equals, and this is the thing I memorize. And I forget it every year, and then when I come back and reteach it, I memorize it. F prime at a, x minus a, plus f double prime of a, x minus a squared. Oh yeah, that's right. There's going to be that factorial thing. 2 factorial, dot, dot, dot. So e to the x at x equals 2 can be approximated by, all right, e squared. E is the function at 2. Derivative at x equals 2. Well, derivative of e to the x, just e to the x, so e squared. X minus, there it is. Everybody gets a little cocky and forgets. X minus 2 plus e squared. X minus 2 squared over 2 factorial plus e squared. X minus 2 to the third over 3 factorial. And if we put in e squared in our calculator and then said, let's find out what's going on, this would get us there. All right, this would get us there. And e squared is kind of pointless because you just, everything drops out. Put in 2, put in 2, put in 2. Hey, we get e squared. Yeah, no kidding. How about, e to the 2.1? This would work. 2.1 minus 2. We'd keep getting closer and closer to what our calculator says. And our calculator is using this to say it. So it's not cheating. It really is the correct answer. So we could write this as sum of, I'm going to use a different variable here, k equals 0. Sometimes it's I, sometimes it's n. To infinity, it's always e squared. And then 0 term, no, 1, 2 factorial, 3 factorial. So that's k factorial. You always check. Plug in 0, no. Plug in 1, yeah. There's an invisible 1 here. Some people really like that. It makes them feel better about life. And then it's 0, 1, 2, yeah, x minus 2 to the k. Got to get yourself into the deep end of the pool on these. They're very challenging. You can't just walk up and say, I think I'll figure this out on the fly. This is tricky stuff. Let me try and give you an example where we center it somewhere else, and we'll end up saying it's the exact same polynomial, just centered somewhere else. Why bother doing that? Because it can really help your calculator or your computing system get to places much faster. Also, we're just conceptualizing what's going on here, so it'll help with that. At 0, it's at 0. The polynomial. And now we start to use this t. Third is 2x to the third minus 3x squared plus 4x minus 5. That was easy. And now life's going to get a little more challenging. What is f of 1? 2 minus 3 plus 4. Sorry, it's hurting me to do all this hard math here. 2 minus 3 negative 1 plus 4, 3 minus 5 negative 2. F prime of 1, I got to do this. 6, 1 squared minus 6 times 1 plus 4, that's dropping out. 6 minus 6, see ya, 4. F second prime at 1 is 12 times 1 minus 6, that's dropping out, 6. And do we need the next one? Third order? I think I do. Even if I don't, never hurts to write it in. That just equals 12. The fourth one is 0, so it doesn't exist. So let's go construct it. All right, to Taylor order. Taylor polynomial, third order Taylor. So we can write T3. T3 of x equals negative 2, the first term, plus derivative 4, x minus 1. I nearly threw a squared in there. That would have been bad. Again, some people like this. I won't be doing that on a regular basis. Plus 2, 4, 6 x minus 1 squared over 2 factorial plus 12 x minus 1 to the third over 3 factorial. So you're probably like, well, that's nice. I don't know what the hell just happened. These are the same. It was just centered at a different spot. So if you were approximating 1.1, this would give you a more accurate answer. 1.1 wouldn't be as accurate. Wait a minute, you just said they're the same. You're right. If I put in 1.1, it'd be the exact same. I was thinking if we had a zillion different terms out here, that'd be different. So if I factored this out and went x to the third minus 3x squared plus 3x squared plus minus 1, whatever I get, and blast it all out, get right there, because 3 times 2 is 6, 12 over 6 is 2, so the coefficient for the first one is 2. And so on and so on. These are the same equation, just centered somewhere else. Yeah, I'm with you. That's just weird. I don't know what you're talking about. All right. Done with note taking. Are we? Yeah, we're done with note taking. Here's the ones you got to memorize. Now, A lot of people squawk when they see this. And yeah, it's a little bit of hard work, but nothing great in life was ever accomplished without hard work. So we did this. This is geometric. 1 over 1 minus x. 1 plus x squared plus dot, dot, dot. And we got an interval of convergence here. That makes sense. Okay. 1 over 1 plus x. Oh, that went from negative to positive, so they just alternate. We just slap this little -1 here. Nothing's changed. All right, that wasn't bad. E to the x. Don't ask me why. I find this very easy to memorize. 1 plus x squared, that's third, and 0 factorial, 1 factorial, 2, 3, 4. Simple to write. Works for everything. Wonder why? Because it's got a factorial on the bottom. Way back in 9.3, we talked about which one grows the fastest. Factorial grows the fastest. So eventually these terms get to freakishly small numbers, which means we can sum them all up. Yeah, I agree. It's weird. Hey, look, a factorial on the bottom, factorial on the bottom. Intervals all reals. You know, factorial on the bottom. And now we got a weird little interval. Sine I memorized because it's odd. This is a hassle, but I kind of work it out. I just kind of figure it out. Notice this is the term, and this is the entire series. Wow, I actually said it right. I'm shocked. Cosine. Then ln of 1 plus x kind of freaks people out a little bit. They're like, well, how the hell am I supposed to know this? Well, I mean, you can just do it from here. Integrate x minus x squared over 2 plus x third over 3. Oh, yeah, that's the same thing. But however, you got to memorize it. And then tangent. Tangent is also an odd function. No factorials, so it only works over a certain range. If you wanted like pi over 4, you'd have to recenter this one. You can't do it with this one. It'll diverge and give you some bizarreness. But yeah, how often do I see this? Not that often. Not that often at all. On the test, on the AP exam. No questions asked. You will have to memorize this, and then you will be given a quiz on it. And if you don't get 100%, you will be given a quiz again on it. So you get 100%. Yep, that's it.